My name is Nathan Goldbaum, and this is Megan Lang. We're both research scientists at the National Center for Supercomputing Applications at the University of Illinois. Our lab is called the Data Exploration Lab, and we're going to be talking about the next generation of particle support in YT. Not everybody is probably familiar with YT, so I'm going to give a few slides discussing just what is YT. YT is the portal between astrophysical simulation formats so astrophysics simulations generally dump large amounts of data to disk in custom formats. So you would, if you wanted to do any kinds of analysis and visualization without YT, you would need to write a reader for this format and then all kinds of code to do visualization and analysis algorithms. YT packages that for you, building on top of the SciPy and Python ecosystem to create beautiful analysis and visualization for many real-world formats. So on the left here, these are logos or example simulation data for many different astrophysics simulation data formats. And YT is also a NUM-focused, fiscally sponsored project. YT is a community of practice. As of June 2017, when I made these slides, we have more than 100 contributors. If you want to know more about how we built up the YT community and how, if you're interested in building a community of practice in your field, there's a very nice paper by Matt Turk, the founder of the YT project, this archive link at the bottom of my slide, about how to scale a code in the human dimension. And all of these people I've highlighted in black here are YT project members. They all have commit bits, and they've all made significant contributions to the code. We have a code of conduct. We have well-defined norms and practices for how to become a contributor and how to become a YT project member. So if you're interested in more in developing YT, please come and talk to us after the talk. So what does YT actually do? So I'm going to give one example here. So the basic YT script at the top on this slide here shows first how to load a data set. So there's this, so you import YT, and then I've also imported something from YT's unit system. And so here, yt.load, isolated galaxy, galaxy 30, galaxy 30 is about a 300 megabyte ENSO data set that YT knows how to automatically parse, how to identify what kind of output it is, and return a data set object that allows you to do interesting things, for example, more kinds of further analysis. So in this example, we create a sphere data object that's centered on the center of the domain and has a radius of 300 kiloparsecs. And we can do some sort of analysis on this sphere. So for example, we can find the mean, min, max, and standard deviation of the temperature field. So for example, if we wanted to know what the temperature is in this galaxy simulation, and print that out, and you can see that you get all of these values, and the value that gets returned by YT also has units attached to it. So YT has a symbolic unit system built on SciPy that is threaded throughout the code. In addition to doing those sorts of quick calculations, like using YT as a calculator on your data, you can also do user-defined fields. So for example, in this example, we define a Mach number field. So that's the velocity magnitude field divided by the sound speed field. Those are two fields that are built into YT. And you just need to write a Python function in order to create new fields that are just algebraic combinations of fields that YT already knows about or that you've defined yourself. And then we can use that field that we defined to load an ENSO cosmological simulation and look at a slice plot. So that means a slice visualization through through this simulation. And show it, and you can see here on the left, that's a slice through the density field, and on the right is a slice of the Mach number field that we defined here. This slice visualization is built on top of Matplotlib, and we try to have very pretty visualizations with units and labels so that you can understand your data and hopefully also a publication quality figure in only a few lines of code. And then finally here, a different kind of visualization, a phase plot. We're also using the feature to select a subset of your data. Here we create we first find the maximum density location in the simulation. Then we create a sphere data object centered on that location with a radius of 10 megaparsecs. And we create a density temperature phase plot. So this is in density temperature space, how much mass is in any given region in that space. So that's sort of what YT is. Next, Megan is going to talk to you about the main thrust of this talk, our new support for particle data in YT.
All right, so Nathan talked a little bit about one of the major tasks that you might want to do with YT, which is selecting a subset of your data. And so for particles or any discrete point distribution, it doesn't have to be astronomy data, you might want to have some sub-selection. Maybe it's a sphere, maybe it's a cylinder, maybe it's a box. And you want to just get the data for those points. So the way YT currently approaches point distributions like particles is to actually treat them as a grid. And this comes as an artifact of how YT started. So YT started as a code for visualizing grid-based astronomy simulations. But then as it expanded to include particle data sets, they needed a way to treat these. And so the easiest way to do this was to actually make the particles look like a grid and then use all of the existing infrastructure that's already there for grids. So for particles, YT currently will build an octree for the 3D particle distribution. I'm showing a quad tree here because 2D is easier on slides. And so you just build up your octree, and then you take the fields defined at the particle positions and paint them onto your octree. So now you have basically grid data that represents what the particle distribution represented. And then you'll traverse the tree in order to get those ocks that are selected by whatever selector you're using and the fields defined at those ocks. So this has advantages in that it used the existing infrastructure and didn't require a whole lot of modification to the code, and it doesn't produce any extra files, so you're just using the data that's already on disk. However, in order to construct this octree, you have to load all of the particles in. And for really large data sets, this is prohibitive. And you have to construct this octree every single time you load that data in. Another con of this approach is that the fields are then defined at cells. So for particle data sets, the natural location to define your fields that the particles represent is at the particle locations. But now we're saying they're at the locations of these cells. And how you map the particle distribution, or the fields represented by the particles, onto these cells will introduce artifacts. So are you saying you're averaging over the particles in a cell? Are you saying you're applying some smoothing? And this is just not a natural way to view particles. So in YT's new approach, which we are calling the Demeshening, we are getting rid of that octree completely and just letting particles be particles. If we return to our problem, we want to load these particles within our selector into memory. And so for large data sets, it makes sense that we only want to load those particles that we need. And so in order to do this, we need to know where those particles are on disk, which can be a little bit tricky, and we'd have to map the entire file, which can be hard for large data sets, like in astronomy. But we can take advantage of the fact that most astronomy data sets are output to multiple files, because you're doing parallel output. And these files are often split in some domain localizing fashion, such as like a Hilbert curve, so that particles within one file are usually in the same space, and particles in another file are usually in the same space. And so here I have two files. The particles in red are in file 1 on the left, and the particles in file 2 are in blue on the right. And we can see that the selector only overlaps one of the files. So in order to get all of the data for this selection, we only need to really load one of the files in the data set. So we just need to track what parts of the domain are touched by each of the files. And we are doing this by using a Morton index. So for those not familiar what a Morton index is, or a Morton order, we divide up the domain into these cells. And each cell has a unique index that can be obtained by interleaving the bits of the index in each of the dimensions. So in this two-dimensional case, we have an x index of 3 and a y index of 2, and then we interleave the bits, and we get a new integer, which is the unique index, the unique Morton index of that cell. And we can do this in any number of dimensions. Our data is usually 3-dimensional, so we use 3-dimensional Morton indices. And if you were to order the indices of these cells, you'd get this pattern, which is the Morton or Z order curve, which is also, if you'll notice, somewhat localized. Not as good as Hilbert, but still good. And so then if you think about a string of bits, as long as that Morton curve, then each cell corresponds to one of the bits along that curve. And we can set that bit to 0 or 1 if it contains particles. And we do this for each file. So then each file will have a string of bits as long as the Morton curve. And where that file contains particles, you set that bit to 1. And where it doesn't, you set it to 0. So in this example, we just have a file 1 in red and file 2 in blue. And you can see that file 1 only has the first 2 bits set, and file 2 only has the second 2 bits set. And so we do this for however many files there are in the data set. But you can imagine that files might collide. So here we have a case where shaded in red are the cells touched by file 1, and shaded in blue are the cells touched by file 2. And we can see there's 3 cells that are touched by both. Excuse me. And in order to handle this, we actually then just nest a second Morton index within those cells with collisions. And we can then resolve these collisions. So now there are no longer collisions between file 1 and file 2. And we do this rather than just refining the entire domain in the first index, because then the bitmaps takes up more space. And so this is a much more compact way of storing that information. And so then to do our selection using these bitmasks, we would just create a selector bitmask, refining at the edges of the selector, and then do a bitwise AND with the file mask to determine which files are actually touched by our selector. So we never have to load in the data once we have the bitmasks. We just compare it with the bitmask doing these bitwise AND operations. And so we can see we select only file 1, and we don't need to load file 2. So in astronomy, we don't just deal with discrete points in particle data sets. We also have these smoothed particle situations where it's basically what it sounds like. It's a smooth particle, so the particle no longer is discrete, and it actually occupies some physical space within the domain. And so if we look, we now see that the particles are smoothed beyond the edges of the cells that they were originally contained in, and so we actually expand our bitmaps to include all of the cells touched by these smooth particles. And then when we do our selection, we will get all of the particles that contribute something to the cells touched by the selector. So now in the smooth particle example of this case, we need to load both file 1 and file 2, because file 2, although it only contributes a little bit, it still contributes some data to those cells in the selector. So as far as implementation goes, I won't dive too deep, but a few notes. The basic procedure that we are following is we create the bitmap indices the first time a particle data set is loaded into memory. And we only have to do this once, so it's a one-time cost. And then we save those bitmaps to a sidecar file, which is also hashed so that if the data get updated, it gets updated as well. And anytime that data set is loaded in the future, you'll load that bitmask into memory first, so then you can do the necessary bitwise AND operations and avoid loading data that you don't actually need. The bulk of the routines are in C++ wrapped in Python to make them fast. And we also use a Python extension of a C++ library for enhanced word-aligned hybrid compressed bitmaps. And we do this because if we just kept the bitmaps as regular bit arrays, it would take up a lot of space on disk, and this saves us a lot of space and still allows us to do all the operations we need. All right, I'll turn it over to Nathan.
Okay, so what Megan described, it actually corresponds to a big change in YT's API. So in particular, the current version of YT and YT 3.3.5 on the left, the data that users get access to when they access a data object, like a sphere or a prism or a disk, the data that they get access to are defined at octree leaf nodes. So we're now talking about, instead of that being the case, now the data are defined at particle locations. So in particular, on the left, there would be n-oct data elements, whereas on the right, there'd be n-particle data elements. So what does that mean in terms of an actual YT script? So here we're loading particle data set. We're asking for all of the data in the domain, and then inside of that data object, we're asking for what is the gas density field. So so what is the gas density field and what is the particle mass field for all of the gas SPH particles in this smooth particle hydrodynamics data set. So in YT 3.3.5, if we ran this script, we'd get the results on the left there. The number of gas density data elements, so that's the number of octree leaf nodes, is some large number. And then also if we ask for the number of particles, you get a different number. So these two things aren't the same. Whereas in the demeshening version of YT, those two numbers are the same. The gas density is defined at the locations of all the gas particles in the simulation. So this is a big change. If we want to do it, we need to consult with the community. So we went through the YT community process for making these sorts of changes, a YTEP, which is short for YT Enhancement Proposal. I think this is a pretty common thing among the SciPy tools. It's based on the process that the CPython community uses, the Python Enhancement Proposal, or PEP process. So if you can go and look at the YTEP that myself, Megan, and Matt Turk wrote earlier this year that describes this change in detail, and is basically a very in-depth version of this talk. So one cool thing that we can do now that we've changed this API is instead of doing the visualization based on the octree, now we have the opportunity to make much nicer visualizations. So in particular, now we in order to make, for example, a slice visualization, which is what these figures show, we can ask for any given particle, what pixels in a slice image does that particle contribute to? And then deposit from the particle onto the image directly. So for example, the image on the right, this particle that we've picked out gets deposited onto onto something like 10 different pixels, depending on how far away those pixels, and the value that it gets deposited depends on how far away that particle is from that pixel. So this is what slices currently look like in YT for particle data. You can see that it's kind of a blocky visualization. We've had complaints from users that our visualizations look blocky for particle data. And people that work with particle data simply don't expect that. It's a Lagrangian method. They don't expect their data to be mapped onto a grid. And for that reason, they don't use YT because they don't like how their visualizations look. So in the new version of YT, the exact same script will produce a visualization that looks like this. Now you can see the contributions of individual particles, and the visualization is much smoother. Let me blink back and forth a couple of times so you can really see the difference. And you can also see, in particular, in low-resolution regions, it makes a lot of difference. So you can see a lot more detail in low-resolution regions because we're not sort of smoothing out that data onto a big octree leaf nodes. So this is another type of 2D visualization, a projection. So here we're integrating through the z-axis of the simulation. This is a different data set that has a galaxy in it. And you can see that, again, the projection visualization is kind of blocky. So now in the demeshening, you can see that you get a much smoother visualization. And actually, if I blink, you can see that there's some things that are sort of popping in and out. That's sort of structures in the simulation that got washed out before because we were smoothing onto a large octree leaf node that had a large volume. So in addition to making prettier pictures, we're also faster now because we can do a number of algorithmic improvements. So for example, for this data set, about a 750 megabyte gadget SPH data set, a projection through the full data set used to take about 2 minutes. Now it takes about 6 seconds, which is a pretty huge improvement. Slices right now are a little bit slower for this data set. We're working on bringing that to either equal speed or faster. Another thing that's much, much faster is if we want to look at a subset, ask what the gas density is in a subset of the domain. For this test that I did earlier, it used to take about 2.5 seconds. Now it takes 650 milliseconds. Just loading the data set as well. The first time is slower because we need to build those bit masks that Megan described. Now, but thereafter, just because we just have to load the bit masks from the sidecar file, it's much faster than it was before. And also, it's now possible to do more things with much bigger data sets. So similar comparison, but now we're doing operations on a 22 gigabyte data set, a much, much bigger data set. So the current version of YT can't even do these visualizations because it's too slow. Just doing the projection through the full data set, it has to smooth the data onto the octree and then project through the octree, and it's just, I waited 10 minutes and couldn't get an answer. Now on this cluster that I did this test on, it took about 150 seconds to do it. So we went from impossible to waiting a little while. So that's a substantial improvement. Slices are faster. Selecting a subset of the domain is much, much faster. And loading and indexing the data set is also faster. So that's it. Are there any questions about what we talked about? And if there aren't any questions, I can do a live demo.
So I have a question if no one else, or you have. Well, so what's on average like? So what on average is the size of these bitmask files? Like, and how are you choosing to do the indexing, and how does that affect the size of them?
So right now you can choose a different order bitmask, so how refined your coarse grid is and how refined your refined grid is where you have collisions. And so it varies a little bit, and what you want to set those values to will depend upon your data. So if you have something that's more clustered, you're going to want a lower coarse order and a higher refined order. If you have something that's more uniform, then you want to do the opposite. And that there's a trade-off there with how large your index gets. Let's see. For the largest...
For that 22 gigabyte data set, with the default index orders for the coarse and refined index, the index is about 2.5 gigabytes. And so that means in order to load the data set, you need about 2.5 gigabytes of RAM. For much, much larger data sets, we're going to explore memory mapping and also basically ways of doing it without keeping the entire index in memory. Right now, the index has to be in memory.
I have a fluffier question. Your YTEP process, you know, it's great and normal, but I'm curious for the specific change. For example, since you were breaking the way that people use YT, did you have any pushback, or was everyone really friendly? How long did it take? Like, what lessons from community development did you learn from that? I know you'd have like many YTEPs, but this one seems like kind of a big one, right?
Yeah, so normally the YTEPs don't necessarily get sent out to the community, to like our users mailing list or like our public communication channels. This one was, because we know it's a big change. I think for the most part, all the feedback we got was extremely positive. There's, in particular, so like for example, the Python 3 process, that had a lot of difficulty because they made a lot of changes, but they didn't make many improvements at the same time. We're trying to, if we do make breaking changes, that comes along with improved prettiness for our visualizations and also speed improvements. One thing that we did get feedback on is that people did want access to the old octree. They want a volume filling mesh that they can deposit onto. So we're going to have an octree data object that we're going to write. So if people were actually using that octree data before, then they'll be able to continue to use that data if they want. A couple months.